Module 2, Environmental Engineering and Sustainable Development. Lecture 1, Introduction to Environmental Engineering. Environmental engineering extends beyond water to include the protection of air, soil, and ecosystems. Its aim is to create sustainable systems that minimize pollution, conserve resources, and improve quality of life. The main areas of concern are solid waste management, air quality control, environmental impact assessment, and sustainable development practices. Lecture 2, Solid Waste Management. Solid waste comes from households, businesses, industries, and agriculture. If not properly managed, it can cause pollution, spread disease, and degrade landscapes. The main steps of solid waste management are: generation, waste is produced by human activity. Collection, waste is gathered from homes and businesses. Transportation, trucks or conveyors move waste to treatment or disposal sites. Treatment and disposal, including recycling, composting, incineration, and landfilling. The guiding principle is the waste management hierarchy: reduce, reuse, recycle, recover energy, and finally, dispose. Lecture 3, Hazardous Waste Management. Some wastes are particularly dangerous because they are toxic, flammable, or radioactive. Examples include industrial chemicals, medical waste, and electronic waste. Managing hazardous waste requires strict regulations, specialized treatment technologies, and secure disposal methods such as lined landfills or high-temperature incinerators. Lecture 4, Air Pollution and Control. Air pollution is caused by emissions from vehicles, factories, power plants, and households. Major pollutants include carbon monoxide, sulfur dioxide, nitrogen oxides, and particulate matter. Control strategies include cleaner fuels and energy sources, filters, scrubbers, and catalytic converters, urban planning to reduce congestion, international agreements to control greenhouse gases. Clean air is vital for preventing respiratory diseases and combating climate change. Lecture 5, Environmental Impact Assessment, EIA. Before new projects such as dams, factories, or highways are built, an environmental impact assessment is required. An EIA predicts the likely effects on air, water, soil, ecosystems, and communities. The process involves baseline studies, prediction of impacts, consultation with stakeholders, and proposing mitigation measures. EIA ensures development is carried out responsibly and sustainably. Lecture 6, Climate Change and Sustainability. Climate change is one of the greatest environmental challenges of our time. Rising temperatures, changing rainfall patterns, and more frequent extreme events affect water resources, agriculture, and health. Environmental engineers contribute by designing renewable energy systems, flood defenses, resilient water supply networks, and sustainable urban infrastructure. Sustainability means meeting present needs without compromising the ability of future generations to meet theirs. It requires integrating economic, social, and environmental considerations into all decisions. Lecture 7, Environmental Health and Hygiene. Environmental engineering also directly impacts human health. Poor sanitation, unsafe drinking water, and polluted air are leading causes of disease worldwide. Promoting hygiene, safe waste disposal, and clean living environments reduces risks of diarrhea, malaria, respiratory illness, and other preventable conditions. Lecture 8, Integrated Water Resources Management, IWRM. A modern approach to water and environmental engineering is integrated water resources management. This approach recognizes that water is a finite resource shared by agriculture, industry, households, and ecosystems. IWRM promotes coordinated development and management of water, land, and related resources, with the aim of maximizing social and economic welfare without compromising sustainability. Lecture 9, Case Studies in Environmental Engineering. Real-world case studies highlight the importance of environmental engineering. The success of Singapore's water recycling program, turning wastewater into high-quality drinking water. The cleanup of the River Thames in London, once biologically dead but now home to thriving wildlife. Waste-to-energy plants in Scandinavia, where municipal waste is used to generate electricity and heat. These examples demonstrate how engineering, policy, and community participation can transform environmental challenges into opportunities. Lecture 10: Future Directions. The future of water and environmental engineering will be shaped by advances in technology and the urgency of global challenges. Emerging trends include smart water grids that use sensors and artificial intelligence for efficient management. Green infrastructure, such as constructed wetlands and green roofs, to improve urban resilience. Circular economy approaches that minimize waste and maximize resource recovery. Stronger integration between engineering, policy, and community engagement. The field will continue to be at the heart of sustainable development and climate resilience. Module 2 Summary. In this module, we explored the broader field of environmental engineering. We studied solid and hazardous waste management, air pollution control, environmental impact assessment, and climate change adaptation. We also looked at sustainability, public health, and integrated water resources management. These topics show how engineering solutions contribute to protecting ecosystems, supporting human well-being, and achieving long-term development goals. Course conclusion. This course on water and environmental engineering has given us a foundation in two interconnected areas. Module 1 focused on water, covering resources, supply systems, treatment, and wastewater management. Module 2 focused on environmental engineering, covering waste management, pollution control, sustainability, and public health. Together, these modules highlight how engineering solutions can ensure clean water, protect the environment, and support sustainable development.